Picture this. Our sun, the engine of our solar system, is on this grand 250 million year lap around the center of our Milky Way galaxy.
Yeah.
That's almost impossible to wrap your head around, isn't it?
Yeah.
And it's that very galactic journey, that immense spin that we're plunging into today.
Exactly. We're going deep into the rotation of our Milky Way using some really compelling recent studies, especially those made possible by the incredible data from the Gaia space mission.
Right, the material you shared.
Yeah, and our goal is basically to extract the most significant and, well, mind-opening insights into how our galaxy actually turns.
Now, you might initially imagine the galaxy spinning like a solid disk, maybe?
Uh-huh.
A giant cosmic record player.
Mm-hmm.
But as with most things on this scale,
Mm-hmm.
the reality is far more nuanced. We're talking about something called differential rotation.
Right. Think of it like our solar system again. The inner planets, they zip around the sun much faster than the outer ones. Similarly, stars closer to the Milky Way center complete their orbits in less time than stars way out in the galactic suburbs. So it immediately throws a curveball into trying to understand the galaxy's overall rotation.
It's kind of like trying to understand how all the performers in a massive rotating stadium are moving when you're stuck sitting in one of the seats.
That's a great analogy.
It reminds me of how the ancient Greeks struggled to grasp planetary motion from their viewpoint on Earth. We're essentially observing this swirling cosmic island from within one of its spiral arms.
And just like those early astronomers, we face some serious challenges in figuring out what we're seeing. But, understanding galactic rotation isn't just some abstract problem.
No.
No, it's absolutely fundamental. It helps us understand where our galaxy came from, how it's structured, the arrangement of stars, gas, dust, and the forces that are shaping its evolution.
Okay, let's start to unpack this then. One of the first hurdles is, well, it's our own movement, right?
Right.
We're not looking at the galaxy from some fixed point outside. We're inside, orbiting the center along with the sun. So our own velocity inevitably affects how we perceive the motion of everything else.
Precisely. And to untangle this, one crucial piece of information we need is Thorals. That's the distance from our sun to the very heart of the galaxy.
Okay, Dorellers.
It's a surprisingly tricky measurement, actually. But recent work, particularly by the Gravity collaboration, has given us a very precise value. $8.12 p.m. 0.003 kiloparsecs.
Wow, 8.12 plus or minus 0.03. That's tight.
It is. And for a bit of perspective, 1 kiloparsec is roughly 3,260 light years. So we're talking about 26,500 light years away from the galactic center.
Wow, okay. That's like trying to navigate a huge city without knowing your own address.
Yeah.
And speaking of our local cosmic neighborhood, there's this idea called the local standard of rest, or LSR. It sounds straightforward, but it gets a little slippery, doesn't it?
It does. The LSR is, well, it's a theoretical concept. It's the average velocity that a group of stars at our sun's distance from the galactic center would have if they were on perfectly circular orbits.
Okay, would have.
Right. The difficulty comes in pinning it down in practice because we have to decide which actual stars to use as our benchmark. Younger stars, for example.
Right.
They haven't had enough time to settle into those nice, stable orbits, so their movements might be a bit more chaotic,
Gotcha. So it's not like there's a clearly marked local standard of rest zone out there.
Not really.
And then we also hear about the solar neighborhood, which sounds kind of similar. What's the difference there?
Good question. The solar neighborhood is generally considered the actual, physical volume of space around the sun, much smaller than the entire galaxy, of course.
Right.
The idea is that within this local volume, we should find a representative sample of the different types of stars and interstellar material present in the galaxy's disk. But the exact size of this neighborhood is a bit arbitrary. It kind of depends on what astronomers are studying at the time. So while the local standard of rest is this theoretical smooth motion, the solar neighborhood is the slightly messy reality around us, where individual stars have their own peculiar motions on top of that general flow.
That makes more sense. Now, solar motion itself, that's our sun's velocity relative to different things around us in the galaxy.
Exactly. And the most common way to define it is in relation to that local standard of rest we just talked about.
Ah, okay.
This difference in velocity is usually broken down into 3 components. 3 of La and the V.
VW sun.
Yeah, subscript sun, vu vada. Think of v dot as the sun's motion towards or away from the galactic center. It's its motion in the direction of the galaxy's spin, like along the orbit. And yen is its motion up or down, perpendicular to the main plane of the galaxy.
Okay, got it. Towards, away, along, up, down. we're starting to get our bearings in this cosmic dance. Now let's talk about the actual rotation speed. We hear about this circular velocity. Theta, what's the key idea there?
Right, theta of r. That's basically the speed an object would need to travel to maintain a stable circular orbit at a specific distance, r from the galactic center, staying within the galaxy's plane.
So the perfect speed for that distance.
Exactly. It's the point where the outward force caused by its motion, the centrifugal force, if you like, perfectly balances the inward pull of the galaxy's gravity at that location, a real cosmic balancing act.
Absolutely. And this leads us to the classical Oort constants, A and B. These sound, well, they sound pretty fundamental to how we understand the galaxy's rotation.
They are indeed very important historically and still useful. These constants, A and B, they're derived based on the idea that the stars in the galaxy's disk are mostly moving in circular orbits around the center,
Okay, circular orbits.
and that the overall gravitational influence of the galaxy is roughly the same in all directions within the disk, what we call axisymmetric.
Axisymmetric, right, like a smooth pull everywhere at a given distance.
Precisely. This is the basis of the Oort-Lindblad model, which was, a foundational framework for understanding galactic rotation.
And physically, what do these constants actually tell us? Like, what do A and B mean? You mentioned an analogy to how fluids move before.
Yeah, that helps.
Yeah.
So the Oort constant A describes what we call azimuthal shear. Imagine layers of a fluid slipping past each other at slightly different speeds.
Okay, like lanes on a highway.
Kinda. In the galaxy, stars at slightly different distances from the center orbit at slightly different speeds, leading to this kind of stretching or shearing motion relative to each other.
Right.
The Oort constant B, on the other hand, describes the vorticity, which is essentially a measure of the local rotation or swirl within the velocity field of the star.
Ah,
So A is about the stretching or pulling apart locally, and B is about the local spinning or swirling motion.
that's a really clear way to put it. And these local Oort constants, A and B, are directly related to the local angular rotation rate of the galaxy, which we call omega zero. Omega zero.
It's right.
And how that rotation rate changes with distance, omega zero prime. Specifically, omega dollar is A minus B, and omega zero is negative A plus B.
That's correct. So if we can measure A and B locally near the sun, we can get a handle on not only how fast things are orbiting in our part of the galaxy, but also whether that orbital speed is increasing or decreasing as we move slightly inward or outward from the sun's position.
Okay, so measuring A and B gives us a local snapshot of the galaxy's rotation. But wait, you mentioned there are complications if the galaxy isn't perfectly axisymmetric. What happens then?
Exactly. And our galaxy isn't a smooth, uniform disk. We have spiral density waves. Think of them like traffic jams of stars and gas moving through the disk,
Okay.
and a central bar-shaped structure made of stars.
Yeah.
These non-axisymmetric features warp the overall gravitational field,
Right, the bar and arms.
which means the Oort constants aren't necessarily the same in all directions you look. That's the azimuth. And they can also depend on how far away the stars you're observing are. So these constants become more like useful local approximations rather than universal fixed values for the entire galaxy at our radius.
So A and B give us a good first approximation, but the real picture is messier because of the galaxy's actual structure.
Yeah.
And you mentioned we can even relax the assumption of purely circular motion. Things aren't always going perfectly round.
Yes. If we allow for stars to have velocities that aren't perfectly circular, maybe they're moving slightly inward or outward, and we still consider a flat disk-like galaxy, we can introduce two more Oort constants, C and K.
C and K.
C describes radial shear, basically, whether stars at different radii are moving towards or away from the center at different rates. And K represents local divergence, whether stars in a small area are generally moving apart or converging.
It sounds like we're peeling back layers of complexity here, getting a more and more accurate picture.
Yeah.
And you hinted at even more advanced models beyond these four Oort constants.
Absolutely. Going beyond these local approximations, astronomers have developed more sophisticated models to describe the velocity field near the sun without making quite so many assumptions about the underlying galactic structure.
Like what?
Well, one of the early attempts was the Okorodnikov-Milne model, which used a mathematical technique called a first-order Taylor series expansion to describe the velocities. More recently, particularly in the 1990s and onwards, astronomers started using things like vector spherical harmonics, a powerful mathematical tool for representing fields on a sphere to describe the overall pattern of tangential velocities of stars. This lets them identify even more intricate systematic motions.
It's incredible how astronomers try to piece together this giant rotating puzzle from our tiny vantage point within it. Okay, Let's shift gears a bit and talk about how our understanding of all this has evolved over time, especially with the arrival of space-based missions like Hipparcos and more recently the game-changing Gaia mission.
That's a crucial point to discuss because before the Hipparcos mission, which operated back in the late 80s and early 90s,
Right, Hipparcos.
our ability to study galactic rotation was really hampered by the limitations of ground-based observations. We could only effectively probe a very small region immediately around the sun. Hipparcos, with its incredibly precise measurements of the positions and proper motions of stars.
Ah, right, proper motions. That's how much they appear to move across the sky over time. Tiny shifts.
Exactly. And Hipparcos gave us much more accurate measurements of these subtle shifts for a far larger number of stars and over greater distances than ground-based telescopes could achieve at the time.
So Hipparcos gave us a much wider and clearer view of our local galactic neighborhood.
Absolutely. It allowed for significantly better estimates of that crucial distance to the galactic center, $2, as well as the sun's velocity relative to the local standard of rest.
And the Oort constants, too.
Yes, it greatly improved our measurements of A and B and helped us develop a more detailed picture of the galactic rotation curve, how the orbital speed changes as you move farther out. It even gave us hints of more complex patterns in stellar motions.
You mentioned an early and important study that used Hipparcos data.
Yes, a really significant early contribution was by Feast and Whitelock back in '97. They used a sample of 220 Cepheid variable stars observed by Hipparcos.
Cepheids. Okay, we'll come back to why they're important.
Definitely. Now, they were working with an assumed value for $200 of 8.5 kiloparsecs, which is slightly different from that newer gravity result we mentioned.
Right, 8.5 instead of 8.1 help.
Based on that, they estimated the sun's velocity components relative to the LSR as $2 around 9.3, $7 about 11.2, and $20 roughly 7.6 kilometers per second. They also calculated values for the Oort constants. 1, equalize plus 14.82 pm, 7.844 sec, and $4 and ISIS 2027 pm, 0.644 anballers in kilometers per second per kiloparsec.
Okay.
And from these, they derived that local angular rotation rate omega dollars is about plus $27 and $99, and its derivative omega dollars as $2 for some cents.
So even back then, with what seems like limited data now, they were starting to get a quantitative handle on the galaxy's spin locally.
Exactly. And this really paved the way for the groundbreaking contributions of the Gaia mission.
Right, because while Hipparcos was a major leap forward, Gaia has provided just a truly transformative flood of data. We talked about this before, but the Hipparcos catalog had only around 280 Cepheid variable stars in total.
Yeah, about that.
In contrast, Gaia's second data release, DR2, contained a staggering 9,575 Cepheids.
It's incredible.
And these aren't just nearby. Well, a good chunk are in the Large and Small Magellanic Clouds. Over 2,100 are spread across the rest of the sky in our own galaxy.
Yeah.
Wow, that's like going from a handful of puzzle pieces to almost having the whole picture.
It truly is. And Cepheids are incredibly valuable for studying galactic rotation. Can you remind us why they're so important again?
Absolutely. So Cepheids are these pulsating stars, right? They get brighter and dimmer. And the really neat thing about them is that the rate at which they pulse their period is directly linked to how intrinsically bright they are, their absolute luminosity.
The period luminosity relation, yeah.
Exactly. So if we measure their pulsation period, which is relatively easy, and their apparent brightness from Earth, we can calculate their distances very accurately, even if they're really far away.
Precisely. They're like standard candles for measuring cosmic distances. And because they are relatively young, massive stars, they serve as excellent tracers of the galaxy's young population and the regions where stars are actively forming, which are primarily in the disk.
And they're bright.
Yep. Their brightness means we can see them at large distances, allowing us to probe the galactic rotation curve far beyond our local neighborhood. We can see out into regions associated with the spiral arms and even the warped outer parts of the disk.
Okay, so Gaia gives us this massive, deep data set of these crucial distance indicators. What have been some of the key discoveries about galactic rotation that have come out of this wealth of information?
Well, one of the early analyses using Gaia's first data release, DR1, was by Bouvier in 2017. He looked at the proper motions of over 300,000 main sequence stars within a relatively small radius, about 230 parsecs from the sun.
Okay, pretty local still.
Yeah, but even in this local sample, the pattern of these apparent motions clearly showed the signature of differential rotation. Bouvier estimated the Oort constants to be $1 is 15.3 pm, 0.4 pm, 0.44 kilometers per second per kiloparsec.
So broadly consistent with the earlier Hipparcos results.
Broadly, yes. But interestingly, he also found significant non-zero values for those higher-order Oort constants we mentioned, C and K. C in dollars was about $3.22, and dollars was about $3.33, both with pretty small errors.
Ah, C and K again. So that suggests.
It highlights that even in our local neighborhood, the galactic velocity field isn't perfectly smooth and axisymmetric. There are these subtle radial motions and divergences going on.
Right, reinforcing that the simpler Oort-Lindblad model is just a starting point.
Right.
What about studies that specifically focused on those valuable Cepheid variables using Gaia data?
There have been several important ones. Bobby-Lev, also in 2017, used a sample of 260 Cepheids from Gaia DR1. He estimated the sun's velocity relative to the LSR as U.0, V.0, 11.73, 7.39 ESRs, plus or minus error bars around 0.6 or 0.7 kilometers. He also derived a rotation curve, assuming a distance R$ of 8 kilometers, that gave a local angular rotation rate. Omega dollars excused 28.84 p.m., 0.333 kilometers kpc, and its derivative, omega dollars excludes 4.05 p.m., 0.101 raters kpc1. This translates to a local standard of rest velocity of about 231 p.m., 66 kilometers per second.
So different studies are getting slightly different numbers, which you'd expect with different data sets and assumptions, but they're generally in the same ballpark. That's reassuring.
Exactly.
What about using Gaia Cepheids to probe the rotation at much larger distances from the galactic center, way out there?
Right, that's where it gets really exciting. Mummeraz and collaborator in 2019 tackled that very question. They used a much larger sample of 773 Cepheids from Gaia DR2, and importantly, they adopted that very precise value for $2 from the gravity collaboration, the 8.122 kpc1.
Okay, using the best distance.
Yes. And with that, they were able to measure the rotation curve out to an impressive 20 kiloparsecs from the galactic center, way beyond the sun.
Wow, and what did they find?
They estimated the sun's rotation speed, theta dollars, to be 233.6 per s p.m., 2.88 kilometers per second. But one of their key findings was about the outer galaxy. The rotation curve beyond about 12 kiloparsecs is remarkably flat.
Flat, meaning the speed doesn't drop off.
Exactly. It shows only a very small decrease in speed with distance, with a gradient of just $1.34 p.m., more 201 kilometers per second per kiloparsec. Basically, things are orbiting almost as fast way out there as they are closer in.
A flat rotation curve.
Yeah.
Now, that's been a major piece of evidence for the existence of dark matter for a long time, hasn't it?
Absolutely. It's the classic piece of evidence. If the visible matter, the stars and gas we can see, were the only source of gravity, we would expect the rotation speed to drop off significantly as you move farther from the center. You know, like Kepler's laws in the solar system where outer planets orbit slower. The fact that the rotation speed stays relatively constant, or decreases only very slightly, implies there's a significant amount of unseen matter, dark matter, in an extended halo surrounding the galaxy. Its gravitational pull is keeping those outer stars moving much faster than they otherwise would.
So the visible stuff isn't enough to explain the speed.
Not even close, especially in the outer parts. And this flatness isn't just a curiosity. It implies the dark matter halo is much more extended than the visible disk, and its density profile must be structured in a very specific way to produce this effect.
That's mind-blowing.
Yeah.
Just watching stars spin tells us about invisible matter. Were there other studies using Gaia Cepheids that supported these findings or looked at different aspects?
Yes, definitely. Kawada and colleagues, also in 2019, found reasonable agreement for the local centrifugal speed derived from about 200 Gaia DR2 Cepheids. Their results match predictions from both the simplified, smooth model of the galaxy and a more complex simulation that included the gravitational effects of the central bar and the spiral arms.
So even with the bar and arms messing things up locally, the overall balance holds.
It suggests that, yeah. While these non-axisymmetric features definitely have local influences, the basic picture of centrifugal balance seems robust.
And what about using these Cepheids to map out the galaxy structure itself, not just its rotation?
Absolutely. Scaron and colleagues in 2019 used a large sample of over 2,400 Cepheids from the OGLE survey, supplemented with Gaia DR2 data, to create a detailed three-dimensional map of the galaxy's young stellar population.
A 3D map based on Cepheids. Cool.
Yeah. And their relatively simple model, assuming star formation happens mainly within the spiral arms, was able to successfully reproduce the observed distribution of these Cepheids. It gave us a much clearer picture of the galaxy's spiral architecture.
So Cepheids aren't just speedometers. They're also like signposts, helping us map the galactic roadways.
Exactly. They're telling us about the galaxy's rotation and helping us map its overall shape.
That's incredible. And other studies seem to be reinforcing these findings about the rotation curve, too.
Indeed. Ablimit and collaborators in 2020 analyzed an even larger sample, around 3,500 Cepheids from various surveys, including OGLE and Gaia. They measured the rotation curve over a wide range from 4 to 19 kiloparsecs.
Yeah.
Their analysis also showed a gently declining rotation curve with a very similar gradient of about 1.33 pm, 0.1 kilometers per second per kiloparsec. Basically the same result as Moaz and his colleagues.
Wow.
So despite using different data sets and analysis techniques, these independent studies are converging on a similar picture of how the outer galaxy rotates. That's powerful confirmation.
It sounds like we're really starting to get a solid, consistent picture of how our galaxy spins, especially thanks to the precision and reach of Gaia's observations. Okay, so how do these detailed findings about galactic rotation connect to our broader understanding of how galaxies form and, well, the crucial role played by dark matter?
These observed rotation curves, particularly that flatness in the outer regions, are really a cornerstone of the current standard model of cosmology, specifically the Navarro-Frank-White NFW profile, which describes how dark matter is thought to be distributed in halos around galaxies.
An NFW model, right?
Yeah. By fitting these theoretical NFW models to the actual observed rotation curve from Gaia and other data, astronomers can estimate fundamental properties of the galaxy's dark matter halo, things like its total mass and its overall size.
And what are some of the key numbers that have come out of this kind of analysis based on the Gaia rotation curve data? What's the scale we're talking about?
Well, based on the interpretation of the rotation curve within the NFW framework, the estimated total virial mass of our galaxy that includes everything, stars, gas, dust, and mostly dark matter, is around 0.82 pm, 0.052 times times the mass of our sun. So nearly a trillion solar masses.
A trillion. Wow.
The corresponding virial radius, which is kind of a measure of how far the gravitationally bound dark matter halo extends, is estimated to be about $191.84 pm, 4.12 kiloparsecs. That's vastly larger than the visible disk.
Much, much bigger than the starry part we see.
Oh, yeah. And furthermore, these models predict the local density of dark matter right here in the sun's vicinity to be approximately $0 R3D3 pm, 0.03 day, or 0.30 TeV per cc.
Okay, still sounds small, but adds up over vast volumes.
Exactly. It means that the vast majority of our galaxy's mass isn't in the stars and gas we can see, but in this mysterious dark matter halo that extends far, far beyond the visible disk.
That's just staggering. So the invisible hand of dark matter is really what's orchestrating the motions we see in the outer parts of our galaxy.
That's the strong conclusion, yes. The analysis of the rotation curve strongly suggests that the dark matter halo becomes the dominant contributor to the galaxy's gravitational pull, and therefore its rotation at distances beyond roughly 12.5 to 14.5 kiloparsecs from the center. Further out than that, it's mostly dark matter calling the shots gravitationally.
It's amazing how studying something as fundamental as rotation can reveal so much about the unseen components of our universe. You also mentioned earlier that the Gaia Cepheid data is proving useful for studying other features, like the warped disk and the spiral arms themselves.
That's right. The precise distances and velocities we get from these Cepheids are invaluable for mapping the three-dimensional structure of the galactic disk. That includes the subtle warp we see in the outer disk, kind of like a bent record, and also the detailed architecture of its spiral arms.
Those are big topics on their own.
Exactly. As you said, these are complex topics in their own right and definitely worthy of their own deep dives in the future.
Absolutely. So much more to explore in our galactic home. So, okay, to bring it all together then, what are the main takeaways from our deep dive into the Milky Way's rotation today?
I think the key things to remember are, 1, the rotation of our galaxy isn't simple. It's differential. Different parts spin at different speeds. 2, the data from Gaia, especially with Cepheids, has been absolutely crucial, a real game changer, for understanding this rotation far more accurately and out to much greater distances.
Okay, differential rotation, Gaia's impact.
3, the analysis of the rotation curve shows it's surprisingly flat in the outer regions. It doesn't drop off like you'd expect from visible matter alone.
The flat curve.
And 4, this flat curve provides compelling evidence for the dominance of dark matter in the galaxy's extended halo. It's shaping how the whole system moves.
It really does bring us full circle back to that initial thought about the ancient Greeks trying to understand the movements of the planets from Earth.
Yeah.
Thanks to incredible instruments like Gaia, we've gone from this very limited Earth-centric view to a much more comprehensive understanding of our place within this colossal spinning galaxy. It's quite a journey.
Indeed. And it beautifully illustrates how much we can learn about the unseen universe just by carefully observing and analyzing the motion of what we can see.
So here's a final thought for you, the listener, to consider. If the dark matter halo, this vast, largely invisible component, is the primary driver of our galaxy's outer rotation, what other hidden influences might be at play? What else might be shaping the structure and evolution of our galactic home in ways we haven't figured out yet?
Mm.
What other fundamental forces or maybe undiscovered particles might be subtly guiding the motions of the cosmos in ways we are only beginning to grasp? It truly makes you ponder the immense amount that remains unknown out there.